Hello, and welcome back to another video. If you've seen my previous videos, you may notice that my voice sounds different. In those previous videos, I was actually using a voiceover service called Well Said. It's an AI that generates a voice from a script. So, decided to go with my real voice and stop using that. So this is what I'll be doing from now on. Today we'll be talking about genetic algorithms, and you may be wondering what that is. It is an algorithm that utilizes gene sequences and simulated populations in order to arrive at a solution for a given problem. Gene sequences, if you're not familiar with those, generally look like this in nature. They are a series of proteins joined together that represent a piece of information. So this may be the color of your eyes, or the color of your hair, or how tall you are, that kind of thing. When creating a genetic algorithm, we generally do something similar. It can look a few different ways, but it'll always match this similar pattern. So in this case, we're using zeros and ones. Each digit represents a piece of information, so it could be, in this case, it'll be a item in a backpack, whether it is actually located in the backpack or if it's been decided not to be packed. So a 0 equals off and 1 equals on, or unpacked and packed. Other ways that you can represent this would be like something like this, where it's a like a hex value kind of thing. So let's say weight is represented by the first two characters, and color is represented by the next 6, and position is represented by the next or the remaining ones. So it's just different ways to encode information, in this case in a string. So today we'll be looking at how to create one of these genetic algorithms in order to determine the best items to take on our day out. So we have a backpack, and in this backpack, let's say we can carry 2.5 kilograms total. We want to maximize the weight limit utilized while also maximizing the value of the items that we are taking with us. Alright, so weight limit is 2.5 kilograms. We have the following items. I'm not going to type all of this out. I will copy paste here, and alright, so we have our items here. You can see we have a bottle of water. It weighs 0.68 kilograms and has a value added of 15. Snacks, 0.13 kilograms and a value of 8. Hat, 0.45 kilograms and a value of 10 all the way down. So as you can see, we have assigned a weight value to each item and a value added value. So in this case, let's say we're going on a hike. Bottle of water has a high value because we stay hydrated. Maybe it's not going to rain today, or it's not expected to rain today, so an umbrella, while we could bring it with, it doesn't add a whole lot of value. So altogether, these items, total weight of all the items is 4.9895187 kilograms. Obviously this is more than the 2.5 kilograms that we're able to carry. So we want our algorithm to come up with different combinations and hopefully find the best combination of items to take that reaches 2.5 kilograms and has the highest value added. So an example combination would be like 0, 1, 1, 0, 0, 1, 0. So in this case, we have snacks, hat, and umbrella. Total weight is 1.95045 kilograms, and total value is 20. Another example combination that we may get is 1, 1, 0, 1, 0, 0, 1. This is bottle of water, snacks, sunglasses, and laptop. This has a weight of 2.2679617 kilograms and a value added of 38. So as you can see, our gene, which is a series of zeros and ones, or a chromosome, or however you want to call it, it has the same length as the number of items that we have here. So we have 7 items. We have 7 zeros and ones in our list here. Again, 0 means that it hasn't been packed. 1 means that it has been packed. So, the different pieces of a genetic algorithm are an individual. So this will be the singular genetic combination, which would be this list of zeros and ones. We have a population, which is a group of individuals. We have a generation, so we might run this algorithm over, let's say, 20 iterations. That would be 20 generations. We need to determine our constraints, which in this case is 2.5 kilograms for our weight total, and then a value to optimize, which in this case is this value property that we have on each of the items. Alright, so let's get into actually coding the algorithm. So I'm going to come down here. So first we're going to import random from, import random. So from random, import random. So this will be for utilizing random number between 0 and 1 in order to do some of the calculations. So now that we have that imported, we're going to define our item class. So this will be like the bottle of water, the snacks, the sunglasses, that kind of thing. So we want to create our initialization function. Self is default. They'll have a name, a weight, and a value, and then just self.name equals name, self.weight equals weight, and self.value equals value. Alright, pretty simple start. So we'll use this as our for our list of items. Next, let's create a individual class. So this will be the individual that makes up a population. So again, class, individual, define the initialization function or method. So self, and then we will take in the list of items a chromosome, which defaults to an empty list, and a generation, which defaults to 0. Self.items equals items. Self.chromosome equals chromosome. Self.generation equals generation. Alright. We're also going to store a value and a weight. So this will be the total value of this individual's combination. So of the total weight of all the total value of all the ones in this individual's chromosome. And for initialization, we are going to set this to negative infinity. So we do this because we are trying to maximize this value, and so since nothing can be lower than negative infinity, we can only go up from there. So the higher the value, the better chance the individual will make it to the next generation. Alright, and then self.weight, we are just going to initialize at 0. Alright, so within this initialization function, so if we are not given a chromosome with a length, so if it's 0, if it's an empty list, then we want to randomly generate the a chromosome for it. So this will be pertinent for our first population, our first generation. So we want to loop over and create a chromosome that is as long as the list of items that we are given. So this is where random comes into play first. So if random is greater than 0.5, so there's a 50% chance of it being higher than 0.5 and a 50% chance of it being lower than 0.5. So if it's higher, then self.chromosome.append 1, and then else self.chromosome.append 0. Alright, so that takes care of our initialization function. Next, we need to define a fitness function. So the goal of this fitness function is to calculate the weight of the individual's chromosome and the value added of the individual's chromosome. We want to take in a weight limit. This is the value that we do not want to exceed. So in our case, it'll be 2.5 kilograms. We are going to create two local variables, weight and value. These will be running sums. So we're going to loop over the individual's chromosome. So for I in range length of self.chromosome, and if the value at position I equals 1, that means that it was loaded, and so we want to take the weight of the item and add it to the weight variable, and the same for the value. So weight plus equals self.items at position I dot weight, and same thing for value, self.items I dot value. Now, if the current weight value is greater than the weight limit, that means that this is an invalid solution. So at this point we want to set self.value equal to float negative infinity. Since nothing can be smaller than negative infinity, this is the worst possible score that it can have. So therefore it'll be less likely to make it into the next generation. And then we're going to return. If we get through this loop and the weight has not exceeded the weight limit, then we want to store the sums. So self.weight equals weight, self.value equals value, and that's it. So if, in general, if your program is not generating the solutions that you desire, the fitness function is where the biggest gains are to be made. Or if it's incorrectly generating solutions, that's generally going to be the fitness function issue as well. Alright, next we want to define the single point crossover function. So this will be the method that determines what the chromosomes are for the next generation. So this will take in another individual. So, yep, other individual. We want to calculate the midpoint of the chromosome and divided by 2. So, alright, this will take the length of the chromosome, which is 7, divided by 2, which is 3.5, and it'll round it to the nearest whole number so that we can use it as an index. So, in this case, I believe it'll round down to 3. But, so next we want to build the child chromosomes. So this will be a list. We'll start by taking the first half of the other individual chromosome, and we will combine it with the second half of this individual's chromosome. So midpoint to end. Then we will do the same in the reverse. So we will take the first half of self chromosome, so 0 to midpoint, and add it to the second half of the other individual's chromosome. Midpoint, end. Alright. Now that we have the 2 new chromosomes, we need to actually create the children individuals. So another list, individual, and we'll pass it self.items, the first child chromosome, and self.generation +1 because this is the next generation. And we will do the same thing for the other chromosome. 1 and self.generation +1. And then at the end we will return the children list. Alright, next up we need to define a mutation function. So what this will do is it'll have a random chance within this rate value that it will flip a chromosome value from 0 to 1 or 1 to 0. So in this case we're passing it, or we're defaulting to 1% chance of the mutation occurring. Generally it'll stick between 1% and 5% when you're determining a mutation rate. In this case we'll just stick to 1%, but for I in range len self.chromosome, so we're looping over the chromosome again. If random number is less than the rate, then if the self.chromosome at position I equals 0, we want to flip it to a 1. And likewise, if it's 0, then we want to flip it to if it's 1, we want to flip it to 0. And that does it for the individual class. Next, we need to build the class for our genetic algorithm. So this will be the class that houses the actual solution generation, and hopefully find a solution to our problem that we present. So class genetic algorithm, define an initialization function, pass itself, and this will just set the default values for our properties. So self.population size is the amount of individuals within a given population. Self.population is the group of individuals. Self.generation is the current generation iteration, and we started at 0. And self.best solution will start it out as none, but this will house the current best solution generated throughout our generations. Alright, so now that we have the genetic algorithm instantiated, we need to define a method that will initialize the population. So this will create the first generation population. This will take in self, population size, and the list of items. So first we want to store the population size that we've been given. We want to also store the items list, and then we want to loop over the list of items. We want to loop for as long as the population size is. So if their population size is 20, then we're going to run through this 20 times. And we want to create a new individual object and append it to the population. So we're just going to pass it self.items. If you remember, it takes in a list of items, chromosome, and generation, but for this initial population, since we're not generating the chromosome for it, it'll just generate its own, and generation starts at 0, so no need to pass that in. Next, we want to call these following two methods, which we'll define in just a moment. But the first one is calculate fitness. This will go through and calculate the fitness on every single individual within the population. And then we want to order the population. So this will order the individuals within the population from highest value to lowest value. So negative infinity will be at the very end of the list, and anything higher than negative infinity will be at the front of the list. And since we've sorted it, that means that the best solution of the generation is the first individual in the population. So it makes sense if it's sorted highest to lowest. That means that the highest value is at index 0. Alright, and now to define the methods that we just used. So define calculate fitness, takes no parameters. For individual in self.population, so we're looping over the population, we call the fitness method on each individual, and we pass it self.weight limit. This is currently not defined up here, but it will be later on. Alright, so that's it for the calculate fitness. Pretty simple. Next, we want to define the order population method. Again, takes no parameters or arguments. It will update the population to be a sorted array, or list, sorry. Well, you're going to use the Python built-in sorted function. Takes a list to sort, a key, which is the value on which to sort. So we are going to use a lambda function here in order to get property of the object, which is the individual, and we are going to return individual.value. And that's it for the order population. Next, we're going to define a helper function, which is select best individual. Again, takes in no arguments. What this is going to do is it's going to compare the current population's first individual against the current best solution value. And if it is higher than the best solution value, then we want to update the best solution to be the current population's first individual. So this is how we ensure that we are always capturing the best solution that our genetic algorithm has generated. Alright. We're going to define another helper function, which is sum values. So what this method is going to do is it will sum up all of the values of the individuals within our population. So sum plus equals individual dot value, and return the sum. We're going to use this in a second in our next function. So def select parent cutoff. So what this is going to do is take in a sum value, which will be using sum values method in order to generate. It will return the index of the parent or individual in the population in which last is added to a running sum. Okay, let me show you. Random value equals random times sum value. So this will generate a random value between 0 and the sum value. And then what we're going to do is create a sum and I variables. These will be incremented. So while I is less than length self.population, so we're looping through the population, and sum is less than this random value. So we are randomly taking a subset of the population and carrying it over into the next population. This ensures that we aren't always taking the absolute best performers, that there's a genetic diversity, so we'll generally get the best performers, but then we'll also have a chance to get the worst performers in there as well. Let's just make sure that our population isn't getting stale and continues to evolve. So self.population I.value, add it to the sum, index plus equals 1 because we're one further, and I plus equals 1. And then we return the index value. So this will be the cutoff point for the population to continue on. So it'll be like 0 to select parent cutoff returned value. Alright. One last helper function before we get to the meat and potatoes of the genetic algorithm. We're going to define visualize generation. No arguments. What this will do is it will print out the current best solution of the population. So it'll just be for informational purposes only, and it'll enable us to see how the population is growing or evolving. So self.generation, we want to see which generation it's currently on, total value of the current best solution of the population. We want to see total weight of the current best solution, best.weight, and then also see what the chromosome is for the best solution. Chromosome. Alright. Now for the fun part. This will be the solve method, which will actually perform all of the steps needed in order to arrive at our desired solution. So self, it will take in a mutation probability, which we will pass to the individual dot mutation method. It will take a number of generations. This will be the number of generations for which to run. A population size. This will be how many individuals should be in each population. And then a weight limit. This will be our constraint, which is 2.5 kilograms. And a list of items for which to pack or not pack. So first we store the weight limit for use in the individual.fitness function, which we call in the calculate fitness method. And then we want to initialize the population. So we pass it population size and the list of items. Once that is generated, we have our population list populated. We have our generation at 0. We have our best solution is the first individual in our generation 0 population. So now we need to essentially repeat all of this for the number of generations. So if we set number of generations to 100, it will run 100 times. So first we calculate the sum of all of our individuals in our population. Then we create a new population list for holding our new population. And then we are going to create a for loop that runs for half the length of our population size. So since each individual can create 2 children, and we want to maintain our population size of 20 or 200 or whatever it is, if we looped over it 1 for 1, it would double the population size each generation. So we loop over for population size and skip every other one. So we are going to create the parents. So we're gathering the index of 2 parents, sum, and self dot select parent cutoff sum. So we have our 2 parent indexes, indices, and now we are going to create their children. So self.population parents 0, so the first parent, we will call the single point crossover method from it and pass it the self.population parents 1, so the other parent. So we have our children. We need them to possibly mutate, so we call the mutation method. Pass it the mutation probability, and do the same thing for the other child. And then we append the new children to the new population. So append children 0 and new population dot append children 1. That takes care of the new population generation. So we store the new population in self.population, and we run self.calculate fitness to calculate the values for each individual, self.order population to ensure that the highest value ones are at the beginning of the list, and then run self.select best individual to make sure that this best solution has the actual best solution if it needs to change. After that, our generation is complete, so we will increment the self.generation value, and then we are going to run self.visualize generation so that we can see what the best solution in that current generation is. Lastly, we are going to print out the best solution overall. So create a title here of best solution, and we want to see the generation in which the best solution was found. Best solution dot generation, and then we want to visualize the total value of that best solution. Just want to see why it's saying self is undefined. That is because this is outside of, so significant space issue. There we are. indented it once. Alright, and now we also want to see the total weight of the best solution. Dot weight. And lastly, we'll see the chromosome, if I can spell it correctly, of the best solution. And since the chromosome is a list of zeros and ones, and it's not particularly readable for humans, we're also going to list the items that were packed. So, items packed. Oh. And we are going to loop through the best solution chromosome in range len self dot best solution dot chromosome, and we are going to, if it was loaded, so if it was packed, we are going to, self.bestsolution dot chromosome. If that equals 1, it means it was packed. So we are going to print out the item name that corresponds to that position. And that completes our genetic algorithm. So, next we are going to create the list of items that we're going to be trying to pack or not. So here we have an empty list, items. We create a new item instance of bottled water with weight and value, snacks, weight and value, hat, weight and value, and so on. We are going to create a variable that stores our mutation probability, our number of generations. We're going to start with 100, population size, and we'll start with 20, and our weight limit, our constraint, is 2.5 kilograms. So we want to instantiate the genetic algorithm and run the solve method on it. So we pass it the mutation probability, pass it the number of generations, the population size, the weight limit, and the list of items. And now, if we run it, this should display the best solution for each generation, and then also display the best solution overall and what items were packed. So we're going to run python backpack.py, and it worked. So here you can see it shows the best solutions. So best solution in generation 1 was negative infinity, so there were no valid solutions proposed in the population. Next generation, best value of 12 and a weight of 1.8. Generation 5, the population got better, a value of 27 and a weight of 2.494761, which is actually the perfect weight, or the most optimal weight in this scenario, though this is not the most optimal value. You can see that for the rest of the generations that was determined to be the optimal, or there wasn't a better solution proposed. So the items packed were bottle of water, hat, umbrella. If we run this again, we can see this time best solution was found in generation 78, total value of 38, total weight of 2.4, and bottle of water, snacks, hat, and laptop. Run this again. Generation 2 found the optimal solution, which is total value of 52, total weight of 2.49, and bottle of water, snacks, hat, sunglasses, and camera. So if you are having issues reaching a desired solution, you're going to want to play around with these three variables. So mutation probability, if we switch that to a 5% mutation, let's run it again. Here we get 44 in 13. Here we get 52 in 57, so perfect solution. 42 and 85, 28 and 42, so there's no real improvement in this case. We'll put that back down to 1%. If we go to population size 200, so this will be more possible solutions in each generation. So let's see, takes a little bit longer to run. Here, best solution, it didn't find any better solutions after the first generation. Value of 20, not very optimal. Next one, 33, 37, 37, 37. So this one is actually underperforming, and it seems that it's always finding this as the optimal solution for it, which is interesting. But if we go and change this number of generations to 1000, then we should virtually always get the perfect solution. Here, generation 24, perfect solution. Generation 22, perfect solution. Generation 200, perfect solution. Generation 6, generation 467. So as you can see, with 1000 generations, it has the time here. It almost reached the 1000 generation mark. But with 1000 generations, it has the time to evolve and figure out the best solution. So yeah, we're going to end it here. If you found this helpful and interesting, remember to leave a like and subscribe. Let me know in the comments what future videos you would like to see. If you have any questions on genetic algorithms or any other topics, just let me know. We'll see what we can do. But yeah, thanks for watching, and have a wonderful day.